Last problem. We're given a ball thrown against a plank that's hanging, and we want to determine the angular velocity of the hanging board after the collision. We did this one in lecture, so hopefully you remember this is an example of conservation of angular momentum. There's no external torques about this rotation point right here. We have the momentum of the ball before the collision, and then the momentum of the ball and the momentum of the rotating plank after the collision. Okay? So we're shown here the velocity of the ball before the collision. We're given the velocity of the ball after the collision. So it bounces off the hanging board with 3 meters per second. So afterwards, it's coming back at 3 meters per second that way. Okay, so that's an important thing. Our point of reference is rotating about is this point A up here. So conservation of angular momentum. Okay, so about point A. So the angular momentum of the ball is a linear momentum times this perpendicular distance of 0.6 meters. So let me write that out as the mass of the ball times the velocity of the ball times we'll call it some distance plus the I omega of the board. We'll call it a plank just to have a different thing here. Okay, and that's going to be equal to mass of the ball, velocity of the ball after the collision times its radius, distance plus I omega of the plank afterwards. So there's what we want to find. Okay, plank's not rotating before, so that's 0. So I'll write it out symbolically just to be a little different here. It's going to be equal to the mass of the board times the radius. Okay, so I'm combining these two terms, and over here, so it's the velocity of the ball before the collision minus the velocity of the ball after the collision. Okay, so I just took this term over to this side, factored out the mass and the radius, because that's not changing, so I get the difference in those velocities, and then I'll divide by I right here. Okay, other key point is this is a vector, so we'll use positive to the right as our convention here. So omega p of the plank afterwards is going to be 0.8, a perpendicular distance of 0.6, okay, and the velocity of the ball beforehand. Actually, I need to be a little careful here. It's sort of obvious the directions. This ball in relation to this point A is sort of a clockwise, counterclockwise rotation if you envision it from point A. So that positive velocity is going to give us a positive angular momentum in relation to point A. So we'll just use the sign of the velocity here, 4. Okay, after it bounces back, that would be a clockwise rotation here. So that's why that value is going to be the -1. Okay, so that's going to be a -3. So there's the most common mistake, is to not get that direction or the sign factored in correctly. And we're dividing through by I. That's given up here. We don't have to calculate that. Sort of got sloppy in my units. Let's go back and fill those in. 0.6 is the radius, so that's going to be in meters, and this is going to be in meters per second, those terms. Alright, so both of kilograms, meters, and meters, so there's my kilograms will cancel out, and 1 meter, 2 meter, meter squared, so units will be radians per second, which is what I would expect. And let's see, calculating that one last time with the calculator. 0.8 times 0.6 times 4 minus a minus 3 is 7, divided by 2.8, so 1.2 radians per second, and the direction of that will be counterclockwise. As shown in the diagram here.